There is a question. Little L2 is the space of sequences, yes, with the Euclidean norm, yes, that's true. And F and G are sequences. It's better at this generality not to use the word sequences, because sequences are used for functions for which the domain is countable. I mean, let me write more specifically. Where's my share? For for a sequence or suite, as you said, usually we write it this way. So either we write it x index n or x of n, the function whose value at the point n. Both are acceptable version. The important thing is that x is defined on n with values on R or C. The domain is countable. And in this case, yes, we can use the word sequence or suite in French. But the way I defined F is defined on omega with values in R or C. The restriction sounds very similar. It means that the sum of absolute value f of x squared x in omega is finite. That's true. If you want to call it the Euclidean norm, I don't mind. That's okay. But we cannot call f a sequence because omega in the general setting is not countable. And if this is not the case, then the word sequence or suite is not suitable for these elements. But they have several properties which are similar to the case of little L2. I defined in the previous page the inner product. So a task is to show that the inner product is well defined. And another task is to show that the norm is complete. These are, I mean, just steps that you need to take. And it's a very good exercise in measure theory to show that L2 of omega is indeed a Hilbert space. The completeness is, I mean, takes a bit of time, but I mean, it's doable. And when you did this, then it's immediate to see that it's actually a reproducing kernel Hilbert space, because for each x in omega, x fixed, absolute value of f of x is less than or equal to the sum absolute value of f of y squared. Y is in our set omega and then root square. Because when we consider all of these y's, one of them is y equal to x, which gives precisely this value. And the one we have on the right side is precisely the norm. So another way to write the same inequality with a different language is to say that ex of f absolute value is less than or equal to the norm of f in L2 of omega. That's the same thing, but written in the language of function analysis. And this means that ex is a bounded functional. And norm of EX as a functional or operator from L2 of omega to our field, which is R or C, is less than or equal to 1. And again, as in the previous case, which was Cn, if we consider the canonical basis, then we see that actually equality holds, but I do not need that actually. The norm of Ex is equal to 1, but I mean, that's enough for us. So we have, therefore, L2 of omega is an RKHS. An RKHS or a reproducing kernel Hilbert space. This is a very good example because it covers many special cases, as we saw before. If omega is just 1, 2 up to n, then we obtain Cn. I mean, I write it here again because it's really important for us. Is omega is equal to 1, 2, and what's happened? Oops. Sorry, I don't know what happened. I try to. Do you see the screen now?
Yes.
Okay, thank you. If omega is equal to 1, 2 up to n, then L2 of omega is our ordinary Euclidean space Cn in the complex case, or Rn in the real case. If omega is equal to n, 1 to up to infinity, then L2 of omega, we usually write L2. Sometimes we want to be more explicit, we write L2 of n, but little L2 without any further indication, it means L2 of n. In our application, because of the Taylor series start in functional spaces, start from 0 up to infinity. So we consider omega equal to n union 0, 0, 1, 2, 3. And this is pretty much the same as above. And it's a bit misleading because even for this one, we write little L2. So it's not a huge source of confusion, but when you see little L2, be careful that we start from 0 or from 1 in the context. And another one which also is used in harmonic analysis is L2 of Z. In this case, we go from minus infinity to plus infinity. So 0 plus minus 1 plus minus 2 and so on. In this case, L2 of omega and is L2 of Z. So these are the important cases that we usually consider in our course. That's not all. I mean, the next step is to consider when omega is not countable. For example, when omega is equal to R. This is a very interesting example to consider, in particular, if you consider this set of functions. Ex defined by this formula, Ex of y is equal to y, to 1 if y is equal to x, and 0 if y is not equal to x. By diagram, this means that at point x, the function is equal to 1, and in all other points is equal to 0. So it's a function like this. And at the first glance, you said, oh, what's the use of this? It's, if we consider the measure theory, Lebesgue measure theory, it's pretty much the same as the zero function, but wait, that's not the case here. The collection Ex when x is in R, you see, it's not countable. It's a collection which the cardinality is the same as the cardinality of R. This is an orthonormal basis for L2 of omega. You see, it could be your first example of a non-separable case that you have a Hilbert space for which you have an orthonormal basis which is not countable. So more explicitly, Ex ET in L2 of omega, it's like Dirac notation is delta xt, which means that if x is equal to t is equal to 1, and if not is equal to 0, and moreover, that's a complete set. It means that their combination is dense in the space. You remember in the previous case, I had, here it is, a diagram like this. F lives here on the yellow part, G on the, H on green part, G on this color. Many different colors you can consider, blue, rose. They are countable. They might have intersection, but on a huge territory, F and or H, they are equal to 0. Now come back here. I say linear combination, and linear combination means finite. Linear combination of Ex is dense in L2. What are these elements? If you look at this, you see, look at this. What is the linear combination? A finite number of these elements. So if I use lin for linear combination of Ax, X is in R. Some books use also span. I also use it, but I try not to use it that much because in many texts, span means linear combination and also topologically closed. I don't want to put the closeness here, just linear combination. Means that elements of this are of this form, alpha 1 Ex1 plus alpha k Exk, when k is arbitrary, alpha k or alpha 1, alpha k are also arbitrary, but a finite number of them. And this element has this form. Here is x1, here is x2, and here is xk. It's alpha 1 here, for example, alpha 2 here, and alpha k there, a finite number of values. And for the rest, which is really huge, is equal to 0. So it's a function which is basically equal to 0, except at finite number of points. And yet, these functions are dense in the space. This way you can understand the complexity of this space. So that is our second example. And it's better to say indeed the generalization of a first example of RKHS. Now we stop studying examples, and we develop certain tools which we need in studying RKHS. So what is a kernel? You remember in the world, in the combination, we have RKHS. We talked about HS, Hilbert space, but we didn't talk about RK, kernel or reproducing kernel. What does that mean? This is connected to duality and Riesz theorem. A bit of preparation to give the definition of kernel. When you have a Banach space X, then its dual X star is the set of bounded linear functionals on X. So everybody is familiar with that. Characterization of X star is very important. And for a few spaces, we know X star, but mostly it's an abstract setting. We know it's a space, we use it, but actually we don't know what it is. Let me see what is the question. The orthonormal basis, the question of Sushil is this: the orthonormal basis of L2 of omega will have a same cardinality as that of omega for any set omega. The answer is yes, because of this. Because of this. Or more generally, did I mention above? Well, I mentioned this just for R, but it's not just for R. This EX is defined for any omega. And the number of EX is the same as the number of omega, or the cardinality of this set is the same as cardinality of omega. So the answer to the question of Sushil is yes. The dimension of this space, put it that way, is the same as the cardinality of omega. So I can add it here. I can add it here, that the dimension as a Hilbert space of L2 of omega, as you said, is the set as the same as the cardinality of omega. But be careful with dimension, the dimension as a Hilbert space, not the dimension as a vector space. The dimension as a vector space is usually higher. Because as a vector space, we should consider Hamel bases, and the number of elements of Hamel bases are very, very bigger. Back to the definition of kernel, we start with X, a Banach space, and X star is the dual. Characterization of dual is important, but not always doable. For some spaces at earlier stages, Riesz, F Riesz gave the characterization, and this is one of his important contributions to the analysis. For example, he showed that in the Lobeck space setting, the dual of LP is LQ for P between 1 and infinity, not including infinity, just between 1 and infinity. And P and Q are conjugate exponent. This means that 1 over P plus 1 over Q is equal to 1. So the dual, he characterized the dual of LP as LQ. And another example that he did, which is very interesting, is the case of continuous function on a compact set K, like unit circle. In this case, the dual is the set of Borel measures on K. I mean, we don't need these details here, but if you ever take a course on measure theory, and sometimes in function analysis, you see these. Two examples. The one we need is about a Hilbert space. And the answer is rather interesting. Again, it's a theorem of F. Riesz. He showed that if we have a Hilbert space, the dual of H, naively speaking, so I write the, what happened to my eyes here? I write the identity with red. We will see momentarily why. But naively speaking, the dual is H itself. This is the contribution of F. Riesz. The dual of the Hilbert space is itself. Why do we need to be a bit careful here? Because his theorem is like that. Fix Y in H. Define the functional lambda from H to C. I consider the complex case, but the real case is the same. Such that here is the definition. Lambda of X is the inner product of X and Y in H. And it is better to call lambda index Y because it depends on Y. So I put a little y here. So lambda y acts on H. Its value on X is the inner product of X and Y. It's very simple. And it's easy. It's just the elementary calculation on the inner product spaces to show that lambda y is continuous. And moreover, its norm, when I say its norm, it means that as a functional from H to C is equal to the norm of Y as an element of H. You see? So therefore, I have been able to find a good collection of functionals on H, indexed by element of H. And this indexing is one-to-one, because if lambda equal y1 is equal to lambda y2, I take this to the other part. And knowing that this is, real linear with respect to the second component, this means that lambda of y1 minus y2 is equal to 0. And this identity tells me that value of y1 y2, its norm equal to 0. So y1 equal to y2. So it's injective. If now I define a map from H to H star, mapping Y into lambda Y, up to here, we know that this map is a one-to-one. And the reason for using a red color here is that it's not completely linear. If you have a complex number here in front of y and it comes out, it becomes, if you have alpha here, its conjugate comes out. You have alpha bar. So it's not completely linear, but that's not a big deal. So the red color is connected to this, and I write in red again here. The mapping is conjugate linear, not complete linear. Well, we can live with conjugate linear. That's not a big issue. What is missing by now to give a sense to this identity? What is missing? What do you think? So if we close our eyes to the conjugate part, we have something which is one-to-one and linear. I mean, keep in mind it's really conjugate linear, but still we cannot say H is equal to H star. Something is missing. And what is missing?
Isometry.
Isometry is addressed. Yes, thank you. I add this. Isometry is addressed here. And thank you. I added here. It's isometric.
Onto part.
I'm sorry?
Onto.
Yes,
Onto.
yes, yes, yes. And that is important. Onto. In other words, there is no other bounded linear functionals. What Riesz constructed here by this formula, it's a functional, it's a collection of functional. Riesz showed that there is no other. And there is no other is equivalent to this, is onto. And therefore, when we put all of this together, we can naively write H is equal to H star. So if I want to summarize, the most important part of this observation of F Riesz is that if lambda from H to C is a bounded linear functional, then there is a unique. The uniqueness is also important. Sometimes I use it. A unique y in H such that lambda is equal to lambda y. Any linear functional is there. So this is something that you can find its proof in many books, including Rudin's book. Why do I need this here? To see why I need here, I go back to the previous slide and go back to the definition of RKHS. I go back, oh, here we are. The definition had three parts: algebraic property, good; topological property, that's good; and then the connection between them. The connection says that EX is a bounded linear functional. Evaluation functional, which is bounded. So I go back to my slide. So if H is an RKHS on omega, by assumption, EX from omega to, I write C, but you keep in mind that it works for real one too. No, sorry, not from omega, from H. Is a bounded linear functional. Therefore, this theorem applies by F Riesz theorem, the theorem that we saw here. There is an element, there is indeed a unique element, which we denoted by k, little k, index x, because it depends on x, in H, such that Ex of f, which is f of x, is indeed equal to the inner product of f and kx in H. That's the beginning of studying kernel. RKHS, the K is for this part. KX, we simply call it kernel, or more in more details, the reproducing kernel for the point X. Point X. And using little k, we also define a capital K. Note that capital K has two variables defined on omega on times omega with its values in C or in R. By simply defining K of X and Y to be the little k y evaluated at point X. That's a definition of capital K. And capital K simply is called the reproducing kernel for H. So capital K is for H. So when we say reproducing kernel for H, we are referring to capital X. When we simply say reproducing kernel or reproducing kernel at the point X, we refer to little k of X. But they are not, two different objects in a sense, because they are closely related by this formula. And now several properties of little k and capital K, and we verify them in the special case we saw before. Let's start with this one. Always keep this formula in mind, this one. F evaluated at X is the same as the inner product of F and Kx. So what is K? I need Ky at point X. You can look at this as a function f. You know that f at point X is f inner product with Kx. Now you replace f by ky. So ky at point x if ky inner product with kx. And now you see another formula for capital K. Therefore, capital K at point xy is defined to be little ky at point x, but it is also the inner product of ky and kx. You need to be careful about the ordering. It's usually a source of mistake, even though in the real case it really doesn't matter, but in the complex case it does matter. For example, let's see what is the relation, capital. What is the relation between capital KXY and capital KYX? Is there any relation between them? Well, we look at the formula with which we have above. K, X, and Y. The ordering says that is little ky and little kx, their inner product. But ky and x is, you change the order of x and y, is little k of x and little k of y. And we know that fg is equal to gf bar. Therefore, we immediately conclude that k of x and y is equal to k, y, and x bar. That's in the complex case. But in real case, we have k of x, y is equal to, it's symmetric in the real case. So it's a function of two variables, which is either having this property or this one. This one is called symmetric, the other one conjugate symmetric. Another consequence of this, we use this formula a lot. Another consequence of this, which is related to Riesz theorem. Somebody mentioned the isometry. Here is the norm of lambda y is the same as the norm of y in H. And we have an incidence of this here. We have Ex of f is the inner product of f and k of x. I write it again below because I will need it when we study Sobolev spaces and other examples. So Ex of f is the inner product of f and kx. Therefore, immediately, we see that the norm of Ex as a functional from H to C is equal to the norm of kx in H. This is a special case of what we wrote above, that the norm of lambda y is equal to the norm of y. Very good, we can continue further. But keep this formula in mind. I will use it several times when we go to examples. What is the norm of kx? Still, we can say a bit more. The norm of kx squared is the inner product of kx and kx. That's the definition of norm. And now we can write this inner product in two ways. Either we can say that this is the function f inner product with kx, So it's the value of this function at the point x. So it's kx evaluated at point x. We can also say that it's the capital X on the diagonal on x and x. Both are correct. And therefore, when we mix this with this formula, we see that the norm of Ex is equal to the square root of Kx of x and is equal to the square root of K at the point of diagonal x and x. So that's another more explicit formula for the norm of Ex. We will see why this formula is important, because usually in operator theory and in functional analysis, it is very difficult to find the precise value of a norm. We define an operator, we show that it's bounded or continuous, even we obtain an upper bound for the norm, but the precise value of the norm, usually we do not know. Even there are celebrated examples in which doctoral thesis was on evaluated the precise value of a norm. I mean, there has been doctoral thesis in Michigan State University on the Riesz projection to find the precise value, or Mashreghi's, I mean, when orthogonal projection, then we send P to P plus, whatever it means, you need a bit of complex analysis. Mashreghi showed that it's a bounded operator, obtain an upper bound, but didn't obtain the precise value. It was obtained way later, also for the conjugation. And here is a case in which we have a functional is an operator. For its norm, we have a very precise formula. We will see when we study the examples that this formula in box is very useful, because we have some operators. If out of nowhere I come and say, okay, find the norm of this operator, probably you cannot do that. But if you keep in mind that it's a reproducing kernel Hilbert space, you can apply this and immediately obtain the value of the norm. We will see. I mean, do not worry about the examples, but we will see that it is doable. So back to our the specific examples that we saw before. We saw Cn. What is the kernel for Cn? The kernel for Cn you have already seen, but under a different name. Now let's find it more explicitly. What do we want to find? We want to find, I mean, fix, say, J in our omega, which is a finite set. What do we want to find? We want to find Kj, an element of Cn, such that for each Z in Cn, if we calculate inner product of Z and Kg, it gives us the evaluation of Z at the point G, or if you wish, Z index G. We want to find this. And it's not difficult to find this. Just look at what is the inner product. Z, either you think it as a function Z at the point 1, at the point 2, at the point n, or as a vector of the dimension n. This inner product in Cn is written this way: Z at point 1, Kg at point 1 bar, plus Z at point 2, kg at point 2 bar up to the last one. That's the definition of inner product. And note that Z1, Z2, and Zn are free. I mean, they can change. Absolutely no restriction on that. It can be anything. And now we have to find kg of 1, kg of 2, kg of 3, such that this identity or this set of identities holds for all possible values of Z1, Z2, and Zn. And this happens if I write this identity this way, you see what should happen. This part, I keep it as it is, Z1 kg of 1 bar. And the other part, I write Z0 times kg of 1 plus 0 up to up to still Z up to ZG times 1 plus last one, which is again no, I'm sorry, I wrote it badly. I write again. I write it this way. I have just one term, ZG. So I write ZG times 1. And all other terms disappear. They are 0. So I write Z1 times 0 plus here plus Zn times 0. So sorry, I should have written it that way. I want this identity to be true for all values of Z1, Z2, and Zn. And you see, because of the freeness, this happens if and only if a kg of I equal to 0, if I is not equal to j, and if I is equal to j, kg of g is equal to 1. Either you think of kg this way, or equivalently, you think of kg as the vector 0, 0, 0, 1 here. That's the j's place. It's the same thing. Either you think of kg as a function as here, or as a vector like here. So I obtain my kernel, my reproducing kernel, but this is not something new. You have seen this before. That's precisely the canonical orthonormal basis that you have seen before. And big capital K, I, and G, what is the formula for this? Again, we have seen this before. This little kg evaluated at point I. And we know what it is. It's written here. If 1, if I is equal to j, and 0 if I is not equal to j. If we think of Kig as an n by n matrix, we can say that K of IG is the identity matrix, because on the diagonal is equal to 1 and elsewhere it's equal to 0. That's the interpretation for Cn. The interpretation for L2 of omega is the same. Precisely what is written here is correct. That's the kernel for L2 of omega, except that our omega is not necessarily 1 to n. It can be any set. So in this case, we already saw the definition of what's going on. In this case, for any x, we already saw the definition of Ex in previous slide. I repeat, Ex of y is 1 and 0 if x is equal to y, if x is not equal to y. And reproducing kernel Kx is precisely equal to Ax for all x. In other words, even in this case, the canonical orthonormal basis is the same as kernel. That's not the case all the time. I mean, we will see different examples, but in little L2, we have this interesting phenomenon. And capital K is the same as identity, but identity on the set omega times omega. If it's n-dimensional, it's an n by n matrix, but it would be an infinite matrix with countable indices or even uncountable one. It's a matrix which is huge, but equal to 1 on the diagonal. Don't have anything here. Cover this. Aha. And now, after the break, I will start talking about a very interesting example, which is a Sobolev space, several different versions of this. And then, I mean, that's the beginning of, indeed, a series of serious examples. I mean, the examples we saw up to now, Cn and L2 of omega, well, they're good, but in a sense, it doesn't show the real power of RKHS. To see the real power of RKHS, we start with good, I mean, at least maybe 10 examples, and each of these examples will take time because I need to explain what is the Hilbert space structure, and then convince you that the evaluation functionals are continuous. And after doing this, I need to find the kernel. And finding the kernel is the biggest task. It's not that trivial. We will see there are some difficulties. In each case, we will cover, try to cover the difficulties and find an explicit formula for the kernel. And by doing this, I mean, after having so many examples, you will be more familiar with explicit examples of RKHS and different applications of this theory. This will take 2, maybe 3 weeks. And in the middle, of course, I will talk about some properties of RKHS2, but my emphasis is on the examples. After that, we enter the more abstract setting. Okay, now, I mean, already feel tired and another stop. Let me stop the